Multithreading and multiprocessing are key techniques in Python for optimizing performance. Multithreading allows multiple threads to run concurrently within a single process, sharing memory space. Multiprocessing, on the other hand, involves multiple processes, each with its own memory space, enabling true parallelism. Understanding these concepts is crucial for efficient concurrent execution in Python. Concurrency in Python allows programs to handle multiple operations efficiently, enhancing performance. It involves managing multiple tasks simultaneously, optimizing CPU usage, especially during input/output operations. Understanding these concepts is crucial for leveraging Python's capabilities in concurrent execution, ensuring programs run smoothly and efficiently. Concurrency involves managing multiple tasks simultaneously, optimizing central processing unit efficiency during input-output operations. It interleaves task execution, allowing progress on multiple fronts. When one task waits for resources, the system switches to another, minimizing idle time and maximizing resource utilization. Concurrency involves tasks interleaving on a single core, creating an illusion of simultaneity through rapid context switching, ideal for input/output bound operations. In contrast, parallelism achieves true simultaneous execution across multiple central processing unit cores, optimal for central processing unit bound tasks. Understanding these distinctions is crucial for effective task management and resource utilization in concurrent systems. Programs are static code on disk, awaiting execution. A process is a running instance of a program with its own memory space, managed by the operating system. Threads, the smallest execution units within a process, share memory and resources with sibling threads, enabling efficient task management within a single process. In process architecture, single process with multiple threads offers shared memory space, lower overhead, and efficient communication, but risks data conflicts. Conversely, multiple independent processes have isolated memory spaces, higher overhead, and require inter-process communication, yet provide better fault isolation. The choice between threading and multiprocessing affects application performance, scalability, and reliability. Multithreading in Python allows multiple threads to run concurrently within a single process, optimizing I/O-bound tasks. Threads share the same memory space, facilitating efficient data sharing, but requiring synchronization to prevent conflicts. This approach is ideal for tasks like web scraping, API calls, and file processing, where threads can efficiently manage waiting times for external resources. Multithreading allows multiple threads to run within a single process, sharing resources and memory. This setup is ideal for input/output bound tasks like web scraping, application programming interface calls, and database operations, where threads efficiently manage waiting times for external resources. However, synchronization is crucial to prevent data conflicts in shared memory. Python's global interpreter lock, GIL, restricts execution to one thread at a time, limiting true parallelism in CPU-bound tasks. This constraint prevents full multi-core utilization, achieving concurrency through context switching rather than parallel execution. The GIL simplifies memory management and ensures thread safety, but poses challenges for CPU-intensive applications. In I/O-bound tasks, multithreading excels by overlapping wait times, as shown in our example. Fetching URLs concurrently with threads reduces execution time compared to sequential processing. This approach leverages Python's threading to achieve significant speedup, demonstrating its effectiveness in scenarios dominated by waiting periods, such as network requests.